Hello, everyone. Welcome back to another episode of From Atoms to Axons
With Ibrahim Shahrur.
and Bilal Hamoud. Now, today we have a guest.
A guest, and let me tell you about this guest. He is out of this world, which kind of brings us to the topic of the day. First of all, our guest, would you like to introduce yourself?
Yeah, my name is David Moutard. I'm a physics PhD at Wayne State University.
That sounds awesome, honestly. That's probably what I want to do in grad school.
When you grow up?
When I grow up, yeah. In the future.
Hey, you know what they say, shoot for the stars.
Oh,
Yeah.
the astro puns are going to be coming in hot today. I can feel
yeah.
it. All right.
All right, so David, let's just dive into it.
Sure.
You're a physics PhD candidate.
Yep.
So tell us about that. You transitioned relatively quickly from your undergrad to your grad school life. You were a physics major and an astronomy major. Now you're doing a PhD. So how's the grad school life compared to the undergrad life?
Good question.
It's different for sure. It's a step up. They do this thing. It's this cool feature they add to a lot of graduate classes where they get harder.
I heard they also get more expensive.
That's sort of the fun thing about doing a PhD in astrophysics, or in physics in general, in a lot of the STEM fields. If you're doing a PhD instead of like a master's or other graduate path, you actually get paid to go to school.
So all of your classes are fully funded.
My classes are funded, and I'm making some additional money on the side.
Very nice. So
And Sorry, go ahead.
do you have to compensate in any way? So
Yeah. So I do have to take on some extra roles. So pretty much all of like the TAs that you might have had in any physics classes, that's what they're doing. They're teaching, and that's the way they're being funded. That's what's paying for their classes. That's what's paying for their food and their rent and the rest of that.
So classes are harder to a lot of people's surprise. Not really.
Right.
What classes are you in?
So this semester I'm catching up on some undergraduate classes that I didn't get a chance to do when I was in my undergraduate. So I'm taking undergraduate quantum 2. I'm taking a graduate math methods course, and I'm also taking a computational physics course, which is just it's like a Python programming to solve physics problems, basically.
Very nice. Very nice. Now, so you're still not taking any astro courses of that kind, or and you're not doing any research so far. Right?
Not yet. So yeah, one of the things is Wayne State doesn't really offer a lot of graduate astro courses, so you kind of have to find the astro where it comes. So focusing on things like nuclear physics, because there's nuclear fusion inside of stars, and so a lot of the astro you have to get from tangents from other class, and that's why my degree, ideally, if I when I finish this, because positivity is important, it'll be a PhD in physics and not astrophysics.
I see.
But your research will be in astrophysics, right?
Yes, if the stars align and everything goes the way it should, then yeah, hopefully I'll be doing some astrophysics, specifically kind of cosmology type research.
Cosmology. Interesting. So you're saying if everything goes according to plan, if the planets align, all 9 of them?
All 9 of them.
All
Well,
9 of the planets align, things will end up in your... Yeah, 9.
Yeah, no,
you're counting on your
yeah, no,
fingers.
I'm-
I feel
I'm-
like you're miscounting.
counting, and that's because my fingers stop at 8 is the thing.
I think your fingers are wrong.
Wait, someone's getting 8, someone's getting 9. What's going on here?
I think that brings us to the topic of the day.
I think that my very educated mother just served us nachos.
My very educated mother just served us nachos with pudding.
Oh, that's would be a gross combo. So that's one strike against your 9-planet argument already. Nachos
So
and
what's that
pudding.
9th planet that we're talking about?
I think we all know, and it's on the list of From Atoms to Axons Do Not Talk list, because folks back home are listening in for the first time. We have a list, Ibrahim and I, of topics we tend not to discuss because whether through emotional passion or disagreement, the conversation is bound to get out of hand, and that includes topics such as morality. Is it relative, is it not? I believe something that's right, he believes something wrong, whatever. Then we get into one of these second topics, which is Pluto. I know, I said it. Pluto. Is Pluto a planet? And if not, what
constitutes a planet?
What jerk of a scientist made it not a planet? And yes, I guess by association we could talk about the constitutions of a planet and what classification systems our wonderful old-timey astronomers gave us to work with.
Yeah, well, so the jerk scientist that made it not a planet is the entire International Astronomical Union. So that jerk scientist is the one.
That punk.
Yeah, there's good reason that Pluto's not a planet. So I do shows at the planetarium, and I talk about this a little bit. And the kind of general way that I say it is, as our telescopes got better and we're able to look out into the farther reaches of the solar system, we saw a bunch of other stuff that was like Pluto. So we saw things like Eris and Sedna and Makemake and all of these other kind of small planet-like things. And so they had to make a decision. They said, well, do we call all of these planets? Do we make it my very educated mother just served us nachos, elephant ears, and and then the abbreviation gets longer. And
Right,
less
which
fun
would
to
be
do.
appropriate if you ate a lot of food, but not otherwise.
Right, yeah.
Okay.
Otherwise, it's just a pain. If you're an elementary student, you have to memorize, 15 planets and get out of here with that.
Right. Wasn't there a brief period where they did require students to start memorizing more than the 9 planets, and they were adding on a couple more?
No,
At least during the initial phase of discovery?
there could be. I don't want to say no. Not when I was learning the planets. I learned 9 planets.
I'm talking about way back when,
Oh,
like
wait.
much earlier when the planets beyond Pluto were discovered as the technology was just getting better. Kind of like the growing pains of it.
I wouldn't be surprised. I don't want to speak on the history because I don't know that much about the history.
I feel like
of it.
I've read that somewhere.
I'll believe you.
The internet doesn't lie, so.
That's always true. Yeah, I found that to be true. But just saying that we found that more planets. So do we call all of them planets, or do we just kick the one Pluto-like thing out? And it's hand wavy, and it's not a really great explanation for why Pluto got kicked out.
So was there a precise definition of a planet before these planets were discovered? Or quote-unquote planets, because we yet don't know what a planet is.
So kind of around this time, they started saying, like, oh, all right, we need to come up with something, right? They're like, this too much is going on right now. We have to come up with something that we can say, like, oh, yeah, it follows this rule, and so it's a planet, right? And so they came up with 3 criteria that you have to pass to be a planet. The first is you have to go around the sun in a regular, predictable way.
Regular and predictable?
Yeah. Your orbit can't be super wonky, and that's getting kind of nitpicky. Some people, like some definitions you read, will just say like has to go around the sun, and like, all right, check. The second criterion is you have to have enough mass to balance out and be in hydrostatic equilibrium. Basically, you have to be a sphere. You have to be shaped like a ball, which Pluto checks that one as well.
Whether it's a gas giant or a solid mass?
Right,
Okay.
exactly. You have to be able to be big enough to pull yourself into a round shape, and that's why like asteroids and stuff are pretty easy because they're these weird lumpy, they're just
So far it's looking good for Pluto, right?
Right.
right, yeah. For checks 1 and 2, the check 3 is where Pluto loses it, and I'm getting angry looks.
I'm just wondering. Please go ahead so
Yeah.
I can tell you you're wrong.
So the last requirement to be a planet is that you have to clear your neighborhood, and I'm saying this with air quotes, clear your neighborhood, because again, it's a hand wavy kind of crappy. It's not a great definition. But you have to clear your neighborhood of similar sized objects, and like that makes sense. Like Earth isn't near anything else Earth sized. That would probably be a huge problem for us. But Pluto, there's all sorts of other stuff. Like I said, we found all of these, like the Eris and Sedna and Makemake, all of this other stuff out there that is like it. And so it didn't quite pass that last criterion.
Now,
So
please go ahead, Abe.
What kind of things were there around Pluto, such as there were these planets that were orbiting the sun next to Pluto? Or were they-
just sort of in the same zone, the Kuiper Belt. There's this region on the far reaches of the solar system. There's all sorts of other Kuiper Belt objects.
So I also heard somewhere that it also is considered not a planet if it crosses orbits with a different planet or a different body.
So you're referring to the fact that Pluto crosses an orbit with Neptune.
Yes.
Right. Yeah, so every once in a while, Pluto kind of cuts off Neptune, and that happens. I've never heard of that being a problem. That's something I think they've known about for some time, and even before it got declassified, people were like, we'll let it slide, right?
I see. So eventually, that jerk scientist, multiple,
The whole
decided that,
committee.
one exception after another, it was eventually time to recall the original idea.
Yeah, absolutely. And I'm going to pull up a picture here. I know pictures make for great radio. But I just want you to go ahead and look at Pluto compared to our moon and tell me which is bigger.
Well, it says the Earth is 8,000 miles across. The moon is 2,100 miles across.
And where's Pluto?
Pluto is 1,400 miles across, so two-thirds the size of the moon.
Oh, sounds wimpy.
Wimpy, but I've seen things much smaller than Pluto, and they could still be considered.
So if I lob a tennis ball into orbit, is that a planet now?
Listen here, David. I don't mean to, cross your qualifications here, overstep my boundaries as a guy who's watched Rick and Morty. I feel like I'm much more qualified, but still, what if there was another solar system out there with a smaller sun, smaller planets, and smaller moons? Is it an arbitrary size, or is it a size reference to other surrounding objects? Just because it's smaller than our moon, does it completely rule it out automatically?
So what you're saying, so if I took like a model of the solar system here, like something you might find in an elementary classroom, and I launched that out of our solar system, so it is no longer in our solar system, would you say that that's still a solar system just because it's scaled down? I guess you get into tricky stuff with, obviously that star's not fusing hydrogen, and it's not
Let's
really
say it
a
is
star.
on that exact scale. You know how they have the demonstrations where it's, yeah. So let's say we take a smaller scale of our universe. Would everything in that universe still be considered a planet? Would the planets themselves be considered planets?
I'm confused by the way you just worded that.
So we have a smaller scale version of our solar system,
Sure.
let's say in a different galaxy. Is it still considered a planet if it's based on its size?
I don't think size comes into it. A big part of it is mass, for sure.
Okay.
Because like I said, you have to have enough mass to pull yourself into a round shape. These things have been sort of arbitrarily made into spheres, right? So I guess my example of saying, a model of the solar system that we put somewhere else is not great at
So you're
best.
saying Pluto is a planet, and you're wrong.
What I will say is I think the definition of planet is trash.
Okay.
I think a lot of definitions in astronomy are just terrible.
Please.
But I think that when the community decides something as a whole, that's what science is. Science is all about classifying things in the broadest sense, right? And sometimes classifications change. And when the community agrees that classifications change, at least the majority of the community, then I think that is the case. If you're in biology and all of a sudden everybody says, I think that this species of dog is this other species, and 75% of them say, I'm good with that, then that's a new classification, and that's fine because that's science. Even if people don't like it, that's just the way that goes.
So now, David, you're on the side of Pluto is not a planet, and really there are no sides here because it's been decided. And Bilal's on the side of Pluto is definitely a planet.
Well, here's the thing. We're talking about these arbitrary rules put in place by a body, and not an elected body, but a body of arbitrary scientists who have come together. I did not make a decision. I was not able to put in my input. And if it's just based off of these scientists, can I assume or can I classify Pluto as a planet, at least in my world?
If you wanted to be considered for these definitions, then maybe get a PhD in astrophysics. And
Is that the first step?
I think that
Yeah,
is the
that's-
first step. Like, I take the stance of someone who doesn't really care that much about classifying whether this object is a planet or not, because at the end of the day, is it useful for astronomers to classify such and such as planet?
It
such
might
as
be
such as
useful
not?
for the people who are learning it in its introductory phases, but later on, probably not.
And that's very much the side that I'm taking. I will agree that the definitions aren't good, but the definitions are the definitions, and in the grand scheme, it doesn't matter whether we call Pluto a planet or a wheel of cheese. You can call it whatever you want. It still is going to do the things that it does.
Mm-hmm. It's not like our classifications have any actual effect on anything outside of our Earth.
And another thing I like to add too, because a lot of people, when I do this in a planetarium show, some people, oh no, Pluto's a planet. I grew up, Pluto's a planet, and so people get kind of huffy about it. And I would like to say to any of those people who might be listening that just because we're not calling it a planet doesn't mean that Pluto's not cool, right? You can not be a planet and still be interesting and cool and fun to learn about and worth researching, and
Especially after we got those most recent pictures of Pluto.
Yeah.
And those look really beautiful.
Oh, absolutely.
Yeah, we're pulling up right now. Oh, man. I hope the audience really can appreciate these photos. I am curious, is there anything that differentiates Pluto from the other bodies that are out there near the Kuiper Belt?
So Pluto has a couple of slightly more interesting, like Pluto has moons, which is cool, right? Like that's already kind of neat. It's one of the more spherical ones. Some of these bodies, I can't think of all of them in my head right now. There's like 6 or so. Don't fact check me on that, or do, because that's what science is about, right? So please,
We're on it.
Not all of them are quite as nicely spherical as Pluto. So Pluto, I mean, it makes sense that people would be up in the air on Pluto, but like I said, it just comes down to what the community agrees on, and I'm just going to go with those definitions, and maybe one day I'll be in the IAU and I'll be able to say, well, I think this is a bad definition and Pluto should be a planet, and then it can change again, and then it still won't matter.
And then they'll revoke your PhD, and it'll be a great time.
Yeah, that's right.
You've heard of civil rights activists. I'm a Pluto right activist.
That's perfectly valid.
Acceptable,
yeah.
in science.
So
So there are 5 moons of Pluto: Charon, Hydra, Nix, Styx, and Kerberos.
Yeah, all.
Isn't one of them bigger than Pluto?
I don't think so.
don't know.
That would shift like a center of gravity thing.
I see.
And then Pluto would become the moon at that point.
Right, because usually with orbits, it's not that the planets are orbiting the bigger object, they're really orbiting the center of mass of the whole system. So even the sun is orbiting the center of mass of the whole solar system, but that center of mass actually lies inside the sun.
Yeah.
So it's not really orbiting in any meaningful way.
Right.
I see. So you did mention about classifications, not just of planets, but of other things in space. Do you want to bring that up?
Yeah. So things in space, I think, in a lot of fields, the classification methods kind of take very logical steps. We were talking a little bit beforehand about biology and how you have this like Linnaean taxonomy system, which can be contentious, and I'm not a biologist, so spare me.
We'll keep that for the biologists
That's
to
right.
mess around with.
But everything follows really kind of top down. It's if you see an animal, you figure out what kingdom it's in and what order and class and phylum and genus and species, and it's a very much top down, a line that you can follow. Here we have more pictures because this is a picture heavy radio show, and what it is it's a chart of all of the different sorts of things in the solar system, and to give you an idea, there's a class of objects called trans-Neptunian objects, and now these can be minor planets or small solar system bodies or dwarf planets or satellites. Some comets are trans-Neptunian objects, but not all of them. All Plutoids are trans-Neptunian objects, but not all trans-Neptunian objects are Plutoids, and it's a mess. It is.
For those of you folks who are also lost, I share in that. I am not an
That's the point. I
That's
think.
the point. Yeah.
The point is that these things are very messy, and there is not like a top-down approach that David was alluding to with, say, the taxonomy of the tree of life or something.
Right, exactly. It's messy, and this might be a limited view, and there might be some astronomers who get mad at me, but I feel like it doesn't have to be messy. We could have like round objects and not round objects, and then follow those in a line down to like.
Square planets.
All of our favorite square planets.
So you would prefer exclusive classifications?
Absolutely,
exclusive
the overlap just makes things confusing, and the more overlap you have, the more confusing it gets. And then these classification systems are supposed to be useful, and the more overlap you get, the less useful I feel they become.
So you mentioned that you give planetarium shows, and so I heard about the way astronomers classify the sky into different zones, and I heard they're called asterisms.
That's a little backwards.
It's backwards. Please.
Yeah, so this is something, it's a fun trick question we like to ask. The pictures that you draw in the sky, the Big Dipper or, Virgo or whatever, these stick figures that you're drawing with the stars, those are asterisms. A lot of people call those constellations.
Yes.
They're not constellations.
They're not constellations. Constellations are the boundaries that surround these asterisms, and those were determined by the International Astronomical Union, our favorite classifiers.
Bilal's not happy.
It leaves a bad taste in my mouth too. But no. So yeah, they have these zones in the sky that it was because these original asterisms were made up by the ancient Greeks, right? And they tell stories with them, and so they have kept them there. They haven't changed anything. They just kind of drew boundaries around where these asterisms are, and that helps you further classify things. If you say, I saw a supernova, and you're like, where? And you can be like, oh, it's in the constellation Virgo, and you know exactly what boundary in the sky.
And they're usually shaped like boxes?
Yeah, they're just these kind of ugly squares that surround these pretty stick figures that you might draw. They're not quite as fun as the asterisms, for sure.
So do you have any fun facts about the sky?
About the sky or space?
The stars, the sky, anything above my head right now, which is most of this conversation.
Oh man, just a fun fact. I have a good Pluto fun fact for you. I don't like the look. I'll tell you, it's a good one though. It's something that'll make you like Pluto more. Pluto has like intermittent seasons, kind of. You know how the Earth has seasons; it gets colder and gets warmer. Sometimes when Pluto gets closer to the sun, it warms up enough to where it can actually like snow and rain. It can make some of the snow, which I think is mostly frozen oxygen. It's really, really, really cold. It's cold enough to make oxygen.
Solid oxygen, you're saying? Or
I want to say that. I feel like that's what I've heard, but like thinking about how I know phases of matter work.
So it would be oxygen in its solid form as snow?
As snow, yeah. And it gets warm enough to where some of that can go up into the atmosphere, and it'll actually start snowing this stuff down. Like,
could it also rain it?
Yeah. Probably if it got warm enough. I don't know if it gets warm enough. But the point is that Pluto has this weather, but only in some parts of the year, because otherwise it's not warm enough. We have this water cycle where it's like water goes up and comes back down and goes up and...
Oh, so kind of like how Michigan is a frozen tundra 9 out of 12 months of the year, and then, normal the other 3.
Yeah, exactly,
Okay.
Except Pluto is a frozen tundra for almost all of it. And then sometimes it's a less frozen tundra, but still pretty frozen. Yeah, it's cold out there.
So, David, in your undergraduate... when you were in undergrad, you did some research in the field of astrophysics, and I'm interested in hearing about the work you did. I heard it's about supernovae.
Yeah.
So tell us more about that.
So the general idea, so starting with what a supernova is, it's basically when a star explodes, and it's a big, bright explosion, and that's, I don't know, kind of the most general way you can say it is star go boom. Right, like that's a supernova.
That's a definition I could work with.
There you go. That's a classification system right there. So these supernova are not only kind of cool because they're these big explosions, and who doesn't like big space explosions, right?
Right.
They can actually be really useful for us. So the research I did was in supernova classification, but it was to be used for cosmology, and cosmology it's always defined in this really like grandiose way, which is the origin and fate of the universe. Like that's what cosmology studies.
But they study dark matter and dark energy and all the stuff in between. So
right. It's study of the universe on the very large scale. So what we want to know is you might have heard before that the universe is expanding, and a big part of understanding the dark matter and dark energy and the way this universe is kind of built you have to be able to understand how it's expanding.
Mhm.
To be able to understand how it's expanding, you have to be able to measure the distances to galaxies. And galaxies are, to give you an idea, the closest galaxy to us is 2 million light years away. And 1 light year is 6 trillion miles. So that is 2 million times 6 trillion miles away, is the closest one to us.
That's a lot of miles.
I
Yeah.
can't wait for that song to come out. 5,000, 2,500, 6,000. Yeah, but for the miles.
For the
a light
miles,
year.
right, yeah.
It's going to be a long class session.
So these things are really far away, so you can't, like slap a yardstick out, right, and like measure it to the next
Cosmic
galaxy.
rulers.
Right. Well, cosmic rulers. We use these things to measure distances, and one of the ways we can do this is something called standard candles. And the idea of a standard candle is like, if I have a 40-watt light bulb and then I walk away until it looks like it's 20 watts to you, you'll be able to tell how far away I am based on how dim the light bulb looks and how bright you know it to be.
Right.
And so some of these supernova are standard candles. They're called Type 1a supernova, and these supernova can be used as standard candles. You can figure out how bright they actually would be if you were standing right in front of it. You could compare it to how bright it looks, and with that you can measure the distance to it. And that's really, really useful because the farther away things get, the harder it is to measure the distance to it.
That's interesting because I use that same concept of brightness to compare myself to Ibrahim because of how bright his future is. I just constantly compare my future to his, and I know how far away I am from him.
Does it follow the inverse square law?
It of course follows the inverse square law. The closer you get to Grandmaster at chess, the further away I get from any hope of ever beating you.
It's funny, we were playing chess just before this radio show.
It was an interesting match where there was 2 queens on one side and
Yeah, I definitely cheated a little bit.
just a little bit, and yet it didn't matter.
No, it was a draw, which is the best I can ask for against Abe here.
Back to Supernova.
Supernova.
Back to Supernova. So the details of my research are not that interesting. Basically, I was looking for a way to classify these supernova without looking at them directly, because the idea is that these Type 1a supernova are really useful for us because they're standard candles. A good chunk of them are not standard candles. But before you can classify them, you've got to watch them for like several weeks and watch how their light changes over time and take a bunch of measurements. And then after 6 weeks of measurements, you find out, oh, we can't use this one, throw it out.
So it's a long process, and it might not yield anything. And
Oh, that sounds like science if I've ever heard it.
oh yeah.
Can you do me a favor?
Yeah.
If you do ever discover a new type of supernova, could you name it a super duper nova for me?
A super duper nova. Yeah, absolutely.
Sweet.
Yeah, no, that's awesome.
I can't wait for this now.
They've gone to like hypernova after that.
Yes.
They totally missed an opportunity.
Wait, they went to hypernova and skipped super duper nova?
Yeah, they went right past it.
How dare they?
That's
right?
blasphemous.
At least an uber nova would sound pretty cool, but no. Wow.
But yeah, so the idea was to look at the galaxy that the supernova lived in, that it happened in, and be able to tell based on the galaxy properties, right? Like if the galaxy was bluer or redder, how bright it was, and to statistically match these things up to what kind of supernova happens. And there are a number of reasons. It's not just like random statistics that some galaxies might yield some types of supernova versus others. And so we found some correlation between galaxy properties and supernova type, which can really, really take down the time. Because if we look at a supernova that's in a galaxy that we know could never ever produce this 1A, this useful supernova, then
You can just scratch that off the list
Right.
immediately. Yeah, that helps a lot.
Yeah, definitely.
So do all stars end up having a supernova at the end of their life, or does it depend?
Oh yeah, it absolutely depends. It's mostly based on the mass of the star.
So let's compare to our sun. What about our sun?
So the way our sun is going to go is in about 5 billion-ish years. It's going to slowly shed out its outer layers and just kind of puff away. It's going to leave something behind called a planetary nebula, which is just puffed out star shells. And it's going to leave behind a core of a star called a white dwarf. You might have heard of white dwarfs before. Now, those white dwarfs are actually what lead to Type 1a supernovas.
So it's the white dwarfs that actually undergo the supernova?
Sort of. So what happens is these white dwarfs can be in a binary system. They can be in a system with another star. And if those white dwarfs are the right distance away, it'll basically start sucking mass off of its counterpart, off of the other star, and then once it gets to a certain mass limit, it goes type 1a supernova. This white dwarf basically can't hold this mass anymore and just sheds it in a violent explosion.
Is there a certain lifespan of a supernova?
I mean, that's a hard thing to say because like there probably is a good answer for it, but you know there's stages of it. You know, the initial explosion might be seconds, but then it's going to kind of slowly just drift away. You know, like the Crab Nebula is a supernova remnant, so that's an object in space. I'm sure almost everybody has seen, even if you can't like say like, oh, that's the Crab Nebula. You've probably seen a picture of it.
Yeah, like where the crab people come from.
Yeah, we're the crab people. Yep, that's it. But yeah, that one's actually cool. And that one happened, or we saw the light from it in like 1056 AD, I think. And there was Chinese and Japanese astronomers, and they were able to look up and they saw this. They thought it was a new star in the middle of the day. It was bright enough when the supernova happened to where they could point up in the middle of the day. And
That's fascinating.
That's kind of unfortunate that it was during the day and they couldn't see it to its full potential. And
well, it would have stayed bright through a couple weeks. I want to say weeks, maybe months. So it stays bright.
Just a lot of light coming in and keeps on coming in and coming in.
And you don't stop coming and don't stop coming.
So if a sun has, if a star has a lot more mass, then what would the end of that star look like?
So if it has a lot more mass, the star will do the other kind of supernova, which we call core collapse. And basically what happens with the core collapse is you have fusion going on in the center of the star. It's basically taking light elements and smashing them together and making heavier elements. And it gets to a certain point where it can't anymore. It starts fusing iron, which has the highest binding energy per nucleon, but that's not important. It starts fusing iron and can't do anymore. Now that fusion is like creating pressure that is pushing outward. It's kind of resisting the gravity of the star because there's a lot of mass, right, trying to pull that star in. So you have this fusion that's pushing out on the outer layers of the stars, and when it stops fusing, those outer layers are allowed to fall in now, and so we call that a core collapse supernova. And it falls in, and there's a violent rebound because now there's way too much stuff and not enough space, and that's how you get the other kind of supernova.
What are the remnants of that? What after that core collapse? Because sometimes you end up with a black hole.
Absolutely,
but other times you don't, and it depends on certain critical mass.
Yeah. So based on the mass, you can get a black hole or a neutron star, which neutron stars are super, super rad.
What is so rad about a neutron star?
So neutron stars, you might be familiar with black holes being super dense and super heavy. But you can't really observe them. That's the whole thing with a black hole. So neutron stars are the densest observable matter that exists.
Beyond, right before black holes, because we can observe them.
Right, we can observe these neutron stars. We can see them, and they would be something like the mass of our entire sun squeezed into the size of like the city of Detroit, or like a city block of Detroit, or something like that. Like
that's so dense.
It's something like a teaspoon of the material weighs as much as like 3 Empire State Buildings.
Oh wow.
Yeah, they're wild. Yeah.
So don't go to the gym. Just grab a teaspoon of neutron stars.
Right, there you go. Neutron stars are really cool.
I assume they're not very stable.
They are actually fairly stable. They stick around for quite a while. They're just dense nuclear matter that's sort of...
It's made up of just a bunch of neutrons, like a lot of neutrons.
Yeah, so it doesn't really have anything that would happen to it that would, rip it apart or make it explode or anything. It just wants to hang out there and be dense.
Sounds like a lot of people.
Well, yeah, that's America.
Well, it looks like we've reached a good point to go for a quick intermission. Join us again at around 6:12 as we tackle some questions from the audience and further go into the details of physics grad school. David, thanks again.
Absolutely.
And Abe.
We'll see you soon.
See you guys.
back. So before we took our intermission, we were talking about core collapse of certain stars that have mass that exceeds a critical mass, and then David told us about how some of them turn into neutron stars, but some of them turn into black holes. So what's a black hole?
So a black hole is an object that is so dense that even light can't escape it, right? So it's like, if I throw something fast enough, I can make it leave Earth. These black holes are so massive that the speed of light is not fast enough to escape it. It's not fast enough to get off. And so that's why they're black, because there's no light coming out of them. Just only partially true, but...
Right. So we don't want to get into Hawking radiation. But just for the enthusiasts out there, turns out that black holes actually do emit radiation if you apply quantum mechanics to them. I think it was Stephen Hawking who first worked it out, and it turns out that black holes actually evaporate, and they give off light, so-called Hawking radiation. And then if you wait really long enough, the black holes will completely evaporate.
Yeah.
They will not stay there.
Yeah. So that's a lot of fun. But black holes have some really cool kind of wonky properties about them. One of the things that's sort of a favorite of any kind of like popular science educator of that kind is to talk about spaghettification, which is what happens if you were to fall into a black hole. The reason it's called spaghettification is because if you're falling in feet first, the gravity pulling on your feet is so much stronger than the gravity pulling on your head that it would just pull you into a thin string of people's spaghetti.
And that's the technical term?
Spaghettification is the actual, as far as I know, nobody's come up with anything better, because how could you come up with anything better?
So there's spaghettification. There's also firewalls. There are black hole firewalls. And that's interesting because, okay, we have the best names in cosmology. Firewalls are sort of the boundary of information for black holes. And so there's Hawking radiation, there's spaghettification, there are firewalls. There's also the thing about time when it comes to black holes.
Yeah, it's definitely a lot of fun because of our good friend Einstein and kind of what his equations do and tell us. It turns out that when you are in super strong gravitational fields, like what you would be in around a black hole, time would actually slow down for you, and the gravity there is so strong that it would essentially stop. So an outside observer would see you get spaghettified, but you would actually just kind of feel yourself slowing down and then stop indefinitely, which is probably way worse a fate than being ripped to shreds. So it's a little more upsetting.
But the idea of time dilation is a crazy thing that was introduced into physics. Well, it was first introduced by Lorentz when he discovered this mathematical trick that showed that, oh, look, time could, in principle, dilate. But he never took it seriously until your boy Einstein came into the scene. And he was like, wait, let's take this seriously and follow the consequences. And yeah, it turns out that you could actually have space contracting, time dilating. So there were these two, I think there were these twins, Scott Kelly, he's an astronaut, and he spent quite some time
in the space station.
In the space station. So technically, according to relativity, one of the twins is actually younger than the others.
Yeah, that's because the one that stayed on Earth was in a stronger gravitational field, and so time moves differently for him. And, when you learn about these things, it's kind of easy to say, like, oh, that's just a funny math trick. Like, that's not real, right? But GPS satellites are far enough away from the Earth to where they actually have to account for this stuff. If GPS can get your location to something like 5 meters, if they didn't account for time dilation, they would be off by like 10 kilometers.
Wow. So
it's a very real measurable effect that they have to take into account. And it's not just a funny math trick. It's, Einstein was definitely a real smart fellow there.
Oh, yeah. And even when we, like, in my research, we do heavy ion collisions. And if you look at those ions as they're going through these tunnels, because they're accelerated to like 99.99999% the speed of light. They're going fast, right? They're actually, they look like pancakes because of this contraction along the direction of motion. So like imagine you've been squeezed all the way down into like this 2D object. That's how they could measure that effect in these collisions. And if you don't take into account relativity, you get the completely wrong answers. You don't make any right prediction.
And one more example of relativity being perfectly true is there are particles that get fired off the sun called muons, and our equations tell us that they should not be able to hit the Earth. They should decay before they ever hit the Earth. But they still hit the Earth all the time, and the reason for that is because they're so small and fast that time is moving at a different rate for them. So we say, you should decay in so many microseconds, and they say we are decaying in that many microseconds just in our frame, which is way stretched out and dilated. And
It's very interesting stuff, and it all works out. It's amazing how the math just works out.
Well, I've been gone for about what I'd consider a light year, but I'm back. So I see you guys were talking about relativity.
We were talking about black holes.
Listen, I
and-
understand a light year is a form of measurable distance, not time, but still, you understand the point.
and a parsec for any Star Wars fan is not a unit of time.
What is a parsec?
A parsec is 3.26 light years. It's also a unit of distance, but he says he does the Han Solo,
Right,
Kessel
Han
Run
Solo,
and
yep.
whatever parsecs.
Yep. So parsec is a combination of two words, right? Like parallax
And arc second.
And arc
yeah.
seconds.
Yeah.
So Star Wars isn't factually correct, here's what you're telling me?
Yeah, believe it or not, actually.
What?
Yeah.
I'm kind of bummed.
All I'm saying is they obviously knew about parsecs, and sure, they didn't have the internet when they wrote that first movie, but they had books.
Right.
You didn't just throw a science word in there and hope it works.
Back in the 80s you did.
They were hoping no one would notice.
Yeah,
Right.
But from atoms to axons is on it.
that's right.
We're fact checking you 40
30
years
years
later.
So we wanted to finish off by talking about grad school. We started off with grad school. Let's finish off by talking about grad school.
Mhm.
There's a lot of people out there who are considering grad school.
And although it may seem like a giant black hole behemoth to address, we can hopefully help you turn that black hole behemoth into a supernova.
That was a beautiful and poetic thing.
Thank you.
Yeah, so
Snaps.
snaps. Yeah, so grad school is hard, and that's something that if you are considering grad school, you should absolutely be 100% aware of, right? Like it gets harder. It does not get easier as the schooling goes on, and they expect more of you. You're going to have more responsibilities. So the important question is that I don't want to say it's for everybody because it might not be, but it's important to weigh these things before you make that kind of decision. You know that you're going to be working harder. They're going to be asking a lot more of you. You're going to have longer days, and you just have to ask where your passion lies. If your passion lies in physics and you want to keep pursuing that path, then absolutely it's worth it. And sometimes I look down at my homework and I would like nothing more than just cry. But you got to remind yourself, like, this is the path that I chose, and I've got to be happy with that. And you have to know for yourself that the hard work is going to pay off.
Right. Once you're done with that homework, if you have this feeling like, oh, I feel good after solving this problem, then you're really passionate about it.
Absolutely.
And you have to have all that motivation. You got to keep going because grad school is very stressful, from what I hear.
Yeah, it's stressful, and a big part of that, like I said, most of us have to TA to get paid, and in physics we're lucky enough to where we can get paid to go to school, and that's huge. I know a lot of other fields, they don't quite have that same kind of funding, and you'll have to pay, which means you're probably also working some other job.
Right. And so the workload just becomes massive.
Right. So and I'm also going to go ahead and say that physics workloads, I haven't taken any other PhD level courses, but from my experience, physics workloads are very intense. Not getting comparative.
I'd say the math alone, like the math homework that you might get, is much, much larger compared to any other form of research you could be doing, just because one problem can take you 10 minutes, but it could also take you a whole day.
10 minutes.
10 minutes. 10 minutes. That's like the first question. What's your name?
Right, yeah. 10, oh, man, how do I spell it?
I've been using numbers for so long.
Yeah, I have a friend who's in med school, and my physics friend and I were like, oh, yeah, we just spent like 6 hours on this problem. It's like, how do you spend 6 hours on a problem? I said, you're in med school. I want you to spend 6 hours on problems. You're going to be my doctor.
Just watch How to Basic for any surgery right before.
Yeah, should cover it.
Got to scramble a few livers to make an omelet.
I can't remember the last time a homework problem took me 10 minutes.
Yeah.
What's the longest a problem's ever taken you
Oh,
that you were able to solve?
That was, I would say something like 3 to 4 hours, especially when it comes to math homework, especially upper level abstract math, because then it's like one sentence question and then the solution is maybe 2 pages. But you got to know how to go from point A to point B and fill in all the details. But say if you're doing a physics problem, then no, here's a question, here's part A, part B, part C, part D, and so you can walk along, you can follow.
Yeah.
But with math, it's
definitely less outline for you.
Yeah.
So, would you say there's no like answer key in the back of the book that you can just kind of quickly reference?
That would make the book suddenly much larger.
But also the problems are not from the book, so
yeah,
forget about that.
Well, props to you guys for taking that on.
Like Abe said, it's incredibly frustrating, and it makes you just want to tear all of your hair out.
But when you finally get Pluto to be a planet,
right,
it's worth it.
The reward at the end.
Absolutely, that's what I'm studying for.
Yeah.
Just one of these days, this math problem is going to help me make Pluto a planet again.
Hey, we're gonna be there all on that day where Abe, Bilal, and David get that Nobel Prize. It's gonna be a lovely day. I don't know what it's gonna be in quite
But
yet.
it's something.
It's something cool. Get ready for it.
So, David, after graduation, do you want to continue on to become a professor?
That's the goal right now. Talking to grad students, you'll learn pretty quickly that grad school beats the desire to do academia out of a lot of people. It's not for everybody, and I'm starting to get that, because I'm teaching now, and I've tutored and taught in a very surface level sense. But this is the first time I've had to do all of the paperwork and grading and the other stuff that comes with teaching. And teaching is super rewarding, right? Like, it feels good to be like, oh, I helped this person understand something. It's a very good, rewarding feeling. What's less good is spending 3 hours after that. All right, grading. All right. And when you also know that you have homework problems that take just as long as grading all of those papers.
Exactly.
Oh wow, yeah. I can't imagine having free time.
It could also be that, after you graduate with a PhD and say, in physics, for example, you're not limited to academia. You have many different options, right?
Oh, absolutely, yeah. With physics, I was told by a physics professor at Wayne State, he's like, oh yeah, once I got my PhD, I could pretty much go do whatever I want. Having a physics PhD basically shows you have incredible math skills and really good critical thinking skills, which is and at in this day and age too, programming. You get really good at coding, and those are 3 skills that applicable to I couldn't go be a doctor, but I could be an engineer or an analyst or a programmer.
Computer,
right?
works
Yeah,
with computer scientists, maybe.
yeah, absolutely.
So you're basically saying grad school can be worth it. It's applicable to multiple settings, and if you are applying for a PhD, then most of the time it'll get covered, the costs. And so, at least at Wayne State in the program that you're in, you are being financially rewarded and academically rewarded. So it's like a win-win.
Absolutely.
And it lets you really focus on your academics. So, food for thought for a lot of people out there who are considering grad school in physics. And if you guys have any questions, as always, you can send a message to me or Ibrahim, and we'll gladly take a look and try and answer it on the next episode of From Atoms to Axons. But as we're approaching the end of our show, I'd like to once again thank you, David, very much for joining us.
It was my pleasure.
Very enjoyable, especially on these topics, astrophysics.
I learned a lot. I have hopes and dreams of you and for Ibrahim as well to rock it with cosmetology. Well, Looks like that concludes our 6th, 7th, 8th,
Some number.
our asterisk number episode of From Atoms to Axons with
Bilal Hamoud.
and Ibrahim Shahrur and David today.
Thanks for having me.
Have a wonderful evening, ladies and gentlemen.